Thank you. So, looks like we've lost the people that like to sit in the stairs, but so as expected, the numbers have dropped a little. Just a reminder that if you are enrolled in the web-based stream for this, you technically are not supposed to be here in the lectures. So ideally, because the face-to-face stream is fully booked and the auditorium has been set for that number of people. Basically, if you're enrolled in the web-based stream, you are not supposed to be in the lectures for going the seats. However, as in my experience, as the weeks go by, generally the numbers drop off a little bit, and so there may be the possibility of spare seats around. As most of you can see now, the lecture hall is still pretty full. This may stay the same if everybody who's enrolled not in the face-to-face continues to come. So I've had the consultation a bit earlier today. A couple of people came through with some good questions. I just wanted to point out some based on some questions from the end of the last lecture as well. The mathematics that we cover in this course, what I covered on Monday, the mathematics in that, you will learn, or hopefully you will learn throughout this course. You're not expected to know that at this point necessarily. So we will go through that. Basically, this course doesn't assume much mathematical background from you. I will have some small assumptions that I will make clear as I go along. Things like hopefully you know what a whole number is, but please feel free to ask if I make an assumption that you're not happy with. Generally, my assumption is based on the sort of the general population. So if there's something that you just don't understand, please by all means ask questions. And if enough people ask the same question, then I'll go back and sort of revisit it. So don't feel necessarily just because you don't understand something that you might be alone in the case. I might have just made an assumption that is not applicable. So I said on Monday that this course is a course on discrete mathematics. I didn't actually mention what I meant by discrete mathematics. It's not mathematics that we're going to keep on the side. We're not going to tell anybody about. It's not that kind of discrete. It's discrete as in discrete, so discrete as in chunks. So as opposed to continuous mathematics, which is probably what a lot of people are familiar with. It's what's usually covered in high school mathematics. It's when you get to calculus and doing all that sort of thing. Discrete mathematics tends to be overlooked a little bit in high school maths, which is a really a bit of a shame, because I find it somewhat easier because it's dealing with things in chunks. It's dealing with things like whole numbers rather than worrying about sort of like limits and things as we look at the continuum. So today we're going to talk about number theory, and number theory is really, if you like, it's where arithmetic meets discrete mathematics. Right? So what do I mean by discrete mathematics in terms of arithmetic? Well, as I said, we deal with whole numbers. We don't worry about fractions. We don't worry about decimals, and so on and so forth. So our main focus for today is going to be solely on what are known as the integers, and that is really what you should be thinking about in terms of this course. And the whole reason we like to do we deal with discrete mathematics and computer science is, well, computers are fundamentally discrete objects. Right? They don't handle continuous transitions. It's basically things are either on or off, and then as you sort of extend that, you sort of have 0 or 1 or 2. You don't have this idea of a half, being partially on, partially off. In the very basic definitions, there are notions of real computing which start talking about the idea of continuous computation, but that is beyond the scope of this course. So anyway, so today I'm going to cover a little bit of basic number theory. And I thought I'd just start with just a quick overview of where this applies, where number theory, all the context, all the things I'm going to talk about today actually applies in computer science, just to sort of give you an idea that although this stuff seems very abstract, it actually has very real applications in computer science. So one of the main applications of number theory in computer science, and that's when you get to really high-level number theory, so like university and beyond, research-level number theory, is in actually the cryptography aspect of things. So you may have heard of RSA encryption or elliptic curve encryption. All those things are based on extensions of the stuff that we're going to talk about today into more complicated or sort of deeper analysis of those things. So cryptography and security, hash functions are also very reliant on some of the things that we're going to be talking about today. Another application that that crops up in computer science with the stuff that I'm going to be talking about today is making large integer calculations. So you may be familiar that an integer on a computer is usually stored in 64 bits, right? Which that ultimately, at the end of the day, puts an upper limit on what the largest integer you have. So in C or in Java, you have a notion of a maximum integer. Whereas, of course, in mathematics, there's no such thing as the largest integer, right? So, why am I stopping at 2 to the power 64 when I could, consider 2 to the power 64 plus 1? Maybe I'm doing something like trying to find the largest prime known or something like this. I have to go well beyond 2 to the power 64. I have to do some computations on what are known as large integers. And some of the ways that we do those computations are dependent on some of the tools that I'm going to cover today. So like modular arithmetic, GCD computations to some degree. A more basic, if you like, application of just some of the things that we're going to talk about today are date and time calculations. So later on we'll be talking about modular arithmetic, and another word for modular arithmetic is clock arithmetic, because basically the idea is that if you keep adding up, you end up going back to 0, right? So you start 1, 2, 3, 4, 5, 6, you get up to 0, which is exactly what happens in the clock, right? You add 12 hours to 1 o'clock, you get back to 1 o'clock again, right? You add 14 hours to 2 o'clock, you're going to get around to 4 o'clock in the afternoon or in the next day. But that's not just restricted to time, it's also restricted to days, right? You add 366 days to January the 1st, and you're going to get January the 2nd on the next year. So all this modular arithmetic, if you have to implement some sort of basic date calculator or time calculator, you're going to be making use of modular functions. I'd say modular functions, mod functions, I should say. Another application for number theory that you may see if you go further into computer science is the idea of solving optimization problems. So again, often an optimization problem from a computer science perspective is going to have a sort of a discrete notion. So you want to say, either this happens or this happens, this happens or this happens. When you turn it into, you can turn it into a continuous one and actually solve it relatively efficiently, but the problem of finding the discrete one is actually quite difficult. And the actual core thing here is integer linear programming. I'm not going to talk very much about that, but that's one area that number theory comes in to answering some questions in computer science. And of course, perhaps the main reason why I'm talking about number theory is it actually provides some very interesting examples for future topics in this course. So hopefully it gives you a nice bridge between things that you're familiar with, and then they'll provide some nice concrete examples of non-trivial results. So often when we introduce a definition, we have something in mind, and you can often have something in mind. It's always useful to have another example to work with so that you can sort of test out some of your basic assumptions to see if they're right or not. So this is these are the main, I guess, points of number theory, and particularly the topics we're going to be talking about today. So today we're going to be talking just as basically a large number of definitions, and just sort of hopefully getting you familiar with the material. There'll be some exercises in the throughout the lecture. That's mainly to give you a few minutes to just to work through them, have a look. If you haven't already had a look at them, try and work through the problem. I've omitted the answers to the exercises in the lecture slides on the web, and those will be updated hopefully today or tomorrow. Somebody already the same thing happened on Monday, and I forgot to make the update, which is now updated. So hopefully the answers will be not too long in coming. But please, pester me on the forums if they haven't appeared. So, but we will go through the answers in the lecture. So just as sort of a start, so the numbers that we're interested in, and the names of the numbers that we're interested in, fall under these categories. You may have seen some of them before, particularly if you've done any mathematics at a university level. So we have the natural numbers, which are 0, 1, 2, 3, and so on, all the whole numbers which are greater than or equal to 0. So in particular, I include 0 in the natural numbers. Most computer scientists include 0 in the natural numbers. A lot of mathematicians don't include 0, but we like to include 0 because we like to think of like empty things are very useful. And so usually the natural numbers are used to represent things like sizes of objects. And so it's very useful to sort of say, right, well, we can have a size of 0, for instance. And a slightly larger set than the natural numbers are the integers, which include the negative natural numbers. So -1 down to -infinity. Well, so minus infinity is not included, but like, and so on and so forth. And then the positive integers. So just in case we don't want to include 0, we'd usually denote it with like n subscript greater than 0, z subscript greater than 0. The textbook actually defines it as blackboard bold P. I don't like using that. It's not a fairly standard notation, and it tends to run into problems when you talk about primes. So for this course, I will only ever denote the positive integers with either n or z greater than 0, like so. So these are what are known as the discrete sets of numbers. They come in chunks, right? So there's 0, and then there's a chunk, and then there's 1, and then there's a chunk, and then there's 2, right? There's very clearly a next natural number from the previous one. The other sets of numbers which are useful, and we will use, but later on in the course. We have the rational numbers, which I talked about on Monday a little bit. And the rational numbers are basically the numbers which can be expressed as the ratio of two integers. So it's m over n, where m and n are integers. And the real numbers, which basically are intuitively, I won't talk too much about how you actually come up with them, but they're the numbers that you can write down with a decimal expansion where you have a finite bit before the decimal point and then a possibly infinite bit after the decimal point. And there are definitions of the rational numbers in terms of the decimal or binary expansion. You can say that a number is rational if its expansion eventually repeats itself, so including 0, 0, 0, 0, 0 indefinitely. So we think of that as just being a finite decimal expansion. But I think it's more useful, it's always more useful to think of rational numbers as the ratio of two integers, because the reason being is that the expansion representation depends on what base you're using. So if you're using base 10, right, these numbers go like this. If you're using base binary, which is base 2, you might get a different expansion. And so people tend to get a little bit confused to say, oh, this expansion goes on forever, whereas this one doesn't, so this one should be rational. The rationality does not depend on the base. Right? Rationality is purely in terms of the ratio of integers. And another thing, just because it has an infinite decimal expansion doesn't mean the number is infinite. Right? So I see a lot of layman mathematicians always sort of say, pi is infinite, and so therefore your phone number is discoverable in pi. Pi is not infinite. Pi is a number between 3 and 4. Right? Pi has an infinite decimal expansion, but all numbers have an infinite decimal expansion. Right? The only thing special about pi's decimal expansion is that it doesn't repeat. Right? That doesn't even mean that necessarily your phone number is going to be in there. Right? We don't know a lot about the decimal expansion of pi. We don't even know if 9 appears infinitely often in it. Right? It could be the case that after a certain point in time, all that's left of the decimal expansion of pi is just 1s and 2s. We actually don't know that. That's a really obscure thing. So when you see things like every conversation you've ever had can be found in the decimal expansion of pi, we don't know. We actually fundamentally don't know that. Anyway, what is important is that natural numbers and integers and positive integers, the symbol is unique, right? So 1 represents 1 represents 1. But for rational numbers and real numbers, the symbols are not necessarily unique. What do I mean by that? Well, so here's a rational number. There's a rational number there. Here's another rational number. Here's another rational number. Right? All these symbols represent the same rational number. Right? So the symbol is not unique. Right? So there's duplication going on there. For real numbers, which you think, okay, now we can get around that. So the decimal expansion of this would be 0.5, and the decimal expansion of this would be 0.5, 0.5. So surely for real numbers it doesn't matter. But actually, I said the decimal expansion of this is 0.5. I was actually lying. The decimal expansion of this is 0.499999, and so on and so on. Right? These are equivalent definitions. These are equivalent decimal expansions of the same number. Right? 0.5 is equal to 0.49999999 indefinitely. Right? Based on how we define, what is this number? How do we define that? We define it in terms of sums of series, and when you compute the sum of the series, you'll get that this thing here is equal to the ratio of 1/2. So even decimal expansions aren't unique. So real numbers and rational numbers don't necessarily have a unique representation. Sometimes we can define it. We can define a canonical one, which sort of says, if it looks like this, then this is. We can reduce it down to looking like this. An example for that for rationals is to sort of cancel out all common factors, right? And so 1/2 would be the canonical representation of a half. But we don't need to worry too much about that. That's just a little bit of an aside. Mostly we're concerned with the natural numbers and the integers. Reals, so you can actually define all these from scratch, and one of my fondest memories of an undergraduate was my third year, second semester of 2. So right at the end of my degree, I did a course called Advanced Topics in Mathematics, and the first thing we did in that course was learn how to count. In the second week, we learned how to add. And it was great. So I was like, go home and say, oh, what did you do at uni today? I was like, I learned how to count. And sort of like, everyone's like, okay, what's that? But basically, what we did was we actually defined what a number was, right? And then we defined what addition was, and we defined what multiplication was in the third week, which was very exciting. but after you've defined those formally based on sort of some fundamental principles, then you can define more interesting things. So for example, what we did was we defined 0 to be the empty set. And if I have a set representing a number n, then the set representing the number n plus 1 is defined as this rather weird thing. So you've got this convolution of sets going on, but you can formally define the numbers in that way, which is again why we like to have 0 as a natural number, because it starts off the whole process. So once you've defined the natural numbers, you can define the integers by throwing in some negatives. Then you can define the rationals by throwing in some ratios. And then, well, then you have to introduce the reals. I wonder if that link works. It should work. Which involves some very complicated mathematics. And I'm not going to talk about what you do and why you do it. But needless to say, basically, once you've defined the natural numbers, you can get everything else, depending on how you want to get it. I've also omitted from here the complex numbers. They just add more complexity, pun not intended. But basically, the idea, so there's always a motivation for why we want to introduce something. So we take the natural numbers and then we say, right, I want to be able to subtract. Right? And so that's fine. Like 2 subtract 1 is fine, but what's 1 subtract 2? What happens when I subtract 2 from 1? And so that gives you the integers. So that's great. We've got the integers. If you've got the integers, you can have multiplication. That's fine. 1 times 2 is still, the multiplication of 2 integers is still an integer. But what happens when you want to divide? And that gives you the rational numbers. And then the rational numbers, so rational numbers are very good. They satisfy a lot of properties. But then what happens when you want to talk about sort of continuity, which is what gives you the real numbers? And then finally, the last step is, well, what happens if you want algebraic closure, right? So the real numbers don't satisfy x squared plus 1 equals 0. There's no x that satisfies that. And so when you add in the ability to do that, that gives you the complex numbers. And then you can go on and do more things, but you start to lose interesting things. Like, for instance, you lose the fact that a times b is equal to b times a. Right? If you start getting more and more complicated ideas. So you have the complex numbers. A guy called William Hamilton developed the quaternions, which was an interesting mathematical exercise. But then discovered that, well, okay, when you've got that, you lose the fact that a times b is necessarily equal to b times a. So sort of people said, oh, well, that can't be interesting. And then computers came along and people discovered that, if we're talking about movement in 3D space, right? If we talk about multiplication as being the composition of 2 moves, so like if I go this way and then this way, right? That going this way and this way is completely different from going this way and then this way, right? I'm completely differently oriented. So suddenly, rotations in 3-dimensional space are not what we call commutative, right? Doing A then B is different from doing B then A. And it turns out quaternions are really, really useful for describing rotations in 3-dimensional space. So they've enjoyed a resurgence in popularity because suddenly computers can very effectively compute things that are normally very tricky, so in working in 3-dimensional space. Anyway, so again, another deviation. So we have. I will talk about sets next week in a little bit more detail. But hopefully this is not too complicated. So when I say the natural numbers, I mean these natural numbers. All right. So they're the basic sets of numbers that we're dealing with. But often it's useful to sort of talk about a range of numbers. And there is a fairly standard notation in mathematics for denoting ranges, right, which are also known as intervals. And so we use square brackets to mean ranges that are inclusive and round brackets to mean ranges which are exclusive. So this is This denotes the set of all things between A and B, including A and B. This is the set of all things between A and B, not including A and B. Right? And then we have, so this is known as closed and open. We have half open intervals. So this is everything that includes A but excludes B, and so on. And likewise, excludes A, includes B. So the French have I think, slightly better notation. They use square brackets all the way around, but instead of using a round bracket, they put a square bracket the other way around. I don't know if that's better. I think it might get a bit confusing. But these are the standard notation, and this applies to any type of number. So if we're talking about an interval of integers, then this is all the integers in this range. If I talk about an interval of real numbers, this is all the real numbers in this range. Right? And there's some more we throw in. So normally A and B have to be numbers, but we can have a special case of infinity and minus infinity, which has always got a round bracket on it, to denote like no lower bound to my range. Right? So this is the set of all things which are just less than or equal to B. Right? So remember, this includes B, but doesn't include anything at the bottom. So important thing to note, right? A and B can also be the same thing. But if they are, then in general this is the empty set, right? It has nothing in it, except if we include A at both endpoints, in which case it is precisely the set containing A. An important thing to note, in our discrete numbers, our discrete sets of numbers, intervals that don't include infinity are finite, right? If m is less than or equal to n, the interval m to n is just the numbers m, m plus 1, m plus 2, up to n. And it will always be finite. So the first exercise, nice quick one to get you warmed up. I'll give you just a minute to just think through the answers. How many elements in each of those two sets?
Are we dealing only in integers or?
Good question. Right? Are we dealing in integers or rationals or reals? How about both? Give me an answer for both. We're clearly not dealing with natural numbers, right? Because minus 1 is not a natural number. So. So, if we're dealing with integers, how many elements in this set? 3. And how many in this one? 1. Yep, good. If we're dealing with, say, the rationals, how many in this set? Infinitely many. And how many in this set? Infinitely many, that's right. Okay? And same with the reals. Right? So, the 3 elements in this set are minus 1, 0, and 1. The 1 element in this set is 0 for integers. But for the rationals and the reals, I can find infinitely many rationals between, say, minus 1 and 0. So there should be no surprise. All right, so that's intervals. The next definition, very useful functions for basically moving from rationals and reals into integers, because that's where we like. That's where we like to work, is the floor and the ceiling function. Right, so the floor function is the greatest integer which is less than or equal to the value x. So the floor of x is the greatest integer less than or equal to x. So if you think if x is a positive number, then basically the floor is what you get by taking away the decimal point, all the bits after the decimal point. Right? The ceiling is like rounding up. It's the least integer greater than or equal to x. Right? So if x is 4, then the ceiling of 4 is still 4, but if x is 4.1, the ceiling of x is 5. Right? So as an example, pi 3.1415926. I'm not going to go anymore. I used to know a few, but I don't anymore. The floor of pi is 3, right? Because 3 is the first, is the integer just the largest integer less than or equal to pi. Likewise, e 2.71828182884. There's a 4 in there somewhere. So 2.7 and a bit. So the largest, the least integer larger than e is also 3. So pi and e are real numbers, but the floor and the ceiling of those two numbers are integers. So you can actually define ceiling in terms of floor, right? Because the floor of minus x is equal to minus the ceiling of x. So as an example, right, so the floor of minus 4.3 is minus 5, right? The ceiling of 4.3 is 5, right? And so minus the ceiling of 4.3 is the floor of minus 4.3. Right? So you don't need to define, you only need to ever define floor or ceiling. You can always define the other ones in terms of that one. You can add integers, so x plus an integer. The floor of x plus an integer is the same as the floor of x plus that integer. You can sort of take integers in and out of these functions, which makes sense because this is shifting it by a fixed amount is not going to change the decimal point, if you like. But a nice observation. I'll start with a simple one, is that the floor of m over k, right? This thing here is equal to the number of, so particularly if m is positive, it's the number of multiples of k that are less than or equal to m, right? Because what is this? This is the floor of m over k, right? So if we imagine our number line here, here's m, right? And we look at the k multiples, k, 2k, 3k, 4k, right? Maybe 5k is over here, right? The floor of m over k is basically what I'm going to do is I'm going to divide everything by k. So this would turn this into 1, 2, 3, 4, and so this is m. Here's m over k, right? 5. Right, if I take the floor, that gives me 4. That corresponds to the number of multiples of k I've got lying before m. Right, starting at 0. So m over k is the number of multiples of k less than or equal to m. So in particular, so n minus 1 over k, the floor of that, this is going to be the number of multiples of k which are strictly less than n. Less than or equal to, yeah, because it's less than or equal to n minus 1, so it's strictly less than n. So if I take the number of multiples of k which are less than or equal to m, and take away all those multiples which are strictly less than n, what I'm left with right, here are all the multiples that are less than m, less than or equal to m. Here are the ones that are strictly less than n. So what's left is the number of multiples of k which are larger than n, but larger than n but smaller than m. Right? So this is very useful for counting things. Fairly standard problem to be set, particularly in exam. And in fact, I think, no, I don't actually have an example for this. There is an example in the practice questions. On that note, I've put up the practice questions I put up a set of practice questions, for the first, well, not for the first two topics, but for numbers, sets, relations. So there's only like 5 questions covering 3 weeks of material. I will probably add to that in the future, but I've just taken last year's practice questions and put them up, and I just need to do some tweaking to get some more of them up for the remaining part of the course. But there are some practice questions up. I will put some challenge questions up in a little while. I've just got to work through and come up with some interesting ones. But if you want to find some more exam type questions, there are some available now, and I'll put up the solutions shortly to those. But anyway, in the meantime, here's another couple of exercises to work through just to get you familiar with the floor and ceiling function, and in particular this question here, which is sort of like, I want you to show that there exists an x and a y such that x plus y is less than, so the floor of x plus the floor of y is less than, strictly less than, the floor of x plus y. So the first ones are just sort of basic computation. The second one is more of the idea of like sorts of things that you can sort of think about coming to this. Coming to this question. So just put the exercises on both screens. So the first question here highlights that, say, 2 times 0.6, 2 times 0.6 is 1.2, right? But if I take the floor of 0.6 first, and then multiply it by 2, and then subtract the floor of, this is the floor of 2 times 0.6, what do I get? Minus 1? Yep. So, because the floor of 0.6, floor of 0.6 is 0. The ceiling of 0.6 is 1. Floor of 0.2 is 1.2 is 1. It's 2. Right. So twice this minus that is going to be minus 1. So the answer to B is minus 1. Well, the first answer is minus 1. Twice this minus this is going to be 0. right? So floor and ceiling functions don't behave very well with respect to multiplication by scalars, right? So that's the important take-home from this. What about the ceiling of square root of 3? 2, right? And the floor is 1, right? You can either get that by knowing that the square root of 3 is 1.7 and a bit, or what you can do is you can say, right, well, 2 squared is 4, 1 squared is 1, 3 lies between 4 and 1, so the square root of 3 lies between the square root of 4 and the square root of 1. And so in particular, this minus this is going to be 1, and that's true for any non-integer. Right? Basically, the ceiling will go 1 up, the floor will go 1 or to the next one down. So as long as you don't have an integer, this will be 1. If you do have an integer, this will be 0. Okay, what about the second one? Any suggestions? Negative 1.5 equal y. Okay, so let's have a look at this. So floor of x is minus 2. Right, this is floor of y. The floor of x plus y, well, this is minus 1.5 minus 1.5 is 3, minus 3, sorry. So this is minus 3. Minus 2 plus minus 2 is minus 4. And minus 4 is strictly less than minus 3. Fantastic. My choice, 2.7 and 2.7. Right, when you round these down, you get 2 and 2. Right, you add them together, you get 5.4. You round that down, you get 5. And the sample solution goes with 3 pi and e for some reason. But you can basically choose pretty much anything as long as if you like, the fractional part adds up to more than 1, which is where the hiccup comes in. So this leads. So that's floor and ceiling. You can have a lot of fun with those functions. Perhaps the most important definition today, and this is the one that people struggle with quite a lot, is the notion of divisibility. So we are talking about integers. We are not talking about rationals. There's no such thing as division in integers. Think of it, that's the best way to think of this, right? So the divides relation is as close as you can get to division, but it is not division. It's a relation. It's something that is either true or false, right? We say m divides n. We write it like this, m vertical bar n. So m divides n, if n is an integer multiple of m. Right? There is no statement about division in this definition. Right? Saying that m divides n if n over m is an integer is not correct, because we're talking about integers. There's no such thing as n over m in integers. This definition is purely to do with integers. So we say m divides n, or n is divisible by m, m is a divisor of n, or m is a multiple of n. Right? They're all the same things. What's important? Why am I emphasizing it as talking about multiplication rather than division? Is that we can talk about n divides 0. Right? N divides 0. N divides 0 for every n. Right? And we can talk about 0. 0 does not divide n, except 0 divides 0. Right? When you talk about division, you can't talk about divide by 0. It doesn't make sense. 0 divided by 0 is nonsensical. Right? You can't define it to be anything and still have normal algebra. But the divides relation is just a yes or a no. Does m divide n? Yes or no? Right? It doesn't give you a number. It's not like add. It's not like multiply. It's not like divide. Right? It's a yes or no thing. It's a relation. And we will see more about relations coming up. And but divisibility forms sort of one of the best examples of a relation that behaves a little bit strangely. Right? So there are a number of relations that you're familiar with, like less than or equal to. Right? Think of divides in the same category. Right? So 4 is less than 3. That's either yes or no. Right? In the case of less than, 4 is not less than 3. Right? It's the same thing with divides. 4 does not divide 3. Right? So think of divides more like less than or greater than sort of thing. Right? So in particular, 1 will divide any integer, as will -1. Right? Because, well, m can be written as m times 1. Right? So m is a multiple of 1 for some integer. Likewise, m divides m, and m divides -m. Because m is equal to -1 times -m. Right? So m is a multiple of -1. N divides 0 for every 0. 0 divides 0. Right? Because 0 is a multiple of 0. Right? I only require one multiple. It doesn't matter that there's lots of multiples. Right? I just require at least one multiple. So there are lots of multiples of 0. And so this is where the divides relation differs from divisibility or division. Right, so that's divides. The next thing that people also get a little bit stuck on is the greatest common divisor and the least common multiple. Right? So m and n just let them be integers. We can talk about all the divisors of m and we can talk about all the divisors of n. The greatest common divisor is the largest number, the largest positive number, which divides m and divides n. Okay, and the least common multiple is on the other side. This is the smallest positive number, which is a multiple of m and a multiple of n. Right? So they're always positive numbers. And if m and n negative, we can just basically ignore the negation signs. So the greatest common divisor of 4 and 6 right, so let's look at the divisors, the positive divisors of 4. Right, so divisors of 4, so 1 is a divisor of 4. 2 is a divisor of 4. 4 is a divisor of 4. Right, the divisors of 6, 1, 2, 3, 6. Okay? So these are the positive divisors. I should just put positive, right? Is 0 a divisor of 4? No. 0 is not a divisor of 4. But -1 is a divisor of 4, right? So on and so forth. -2 and -4. In fact, there are only 6 divisors of 4. Right, so we look at all the common divisors. So 1 is always a common divisor of everything, right? Because 1 divides everything. But 2 is also a common divisor. And then 3, 4, and 6, well, 3 and 6 are divisors of 6, and 4 is a divisor of 4 only. Right, so the greatest common divisor of 4 and 6, GCD of 4 and 6, is 2. Right, and as I said, we can do that. So GCD of -4, right? The positive divisors of -4 are the same as the positive divisors of 4, right? So we can do plus or minus 4, we can do plus or minus 6. Right, we're always going to get the same. What about the multiples? Let's look at the multiples, the positive multiples of 4. Right. So 4. 0 is a multiple, but not a positive multiple. 8, 12, 16, so on. Positive multiples of 6, 6, 12, 18, 24. 24 is in there as well. Right, so we look at the common multiples. Right, 12 appears in both lists, 24 appears in both lists. Right, so the LCM, the least common multiple of 4 and 6, right, lowest positive multiple, right? Because remember, 0 is a multiple, so that would be small. That would be lower, but we don't want 0. So the least common multiple of 4 and 6 is 12. So now that we've got divides and we've got LCM and GCD, we can talk about what a prime number is and what relatively prime numbers are. So a prime number is a number which is greater than 1, an integer which is greater than 1, that is only divisible by plus or minus 1 and plus or minus itself. Right? There are other definitions of prime. This is the one in the book that I'm going to go with. And we talk about relatively prime numbers if they have, so two numbers are relatively prime if they have no factors in common apart from 1. Right? No positive, plus or minus 1. So the GCD of those two numbers is 1. Relatively prime numbers are very useful for when we're doing modular arithmetic, but that's something that we'll explore, I think, at a later time. Prime numbers are, of course, very useful for doing things like crypto and so on. But this is the definition of prime that we're going with in this course. Finally, one last function to help ease things is the absolute value function. This is basically forget the negative sign if there is a negative sign, right? So if x is positive, then you don't do anything. If x is negative, then you take the negative of it. So two negatives will give you a positive. So like the absolute value of minus 5 is minus 5, which will give you 5. This is why it looks a bit weird, like minus x if x is less than 0. But if x is less than 0, minus x will be positive. Right? And so we've got a lot of bars going on, right? Single bar meaning divides. 2 bars on the outside meaning absolute value. Usually the context makes it clear. Try and keep things clear. Do big lines. The divides line should be a lot bigger than the absolute value line. So like if you said absolute value of m divides the absolute value of n, you would sort of put a big line through there. But an interesting observation, and it can go with a different definition of GCD and LCM, it's very easy to show, is that if you multiply the GCD and the LCM together, it's the same as the product of m and n when you take things positively. Right? So going back to the previous example, so the GCD of 4 and 6 was 2, the LCM is 12, 2 times 12 is 24, which is the same as 4 times 6. Right? But of course this could have been plus 4, this could have been minus 4 and minus 6, or sorry, minus 4 and plus 6, and then minus 4 times plus 6 is minus 24, so that's why we take everything positively. Right? So just consider everything positively, and you can try this out, you can try this. I think it's worth trying out a few examples, plugging in m and n, computing their GCD, computing their LCM, and just seeing for yourself that if you multiply those two numbers together, you get m times n. So next set of exercises, again, get you familiar with divides. So true or false, when I say true or false in this case, I mean sometime, is it always true? Is it always false? Is it sometimes true? Is it sometimes false? So when we say explain briefly, that's what I mean. So it's like, is this always true? Is this always false? So does n divide 1? True or false? Always false? Right, n equal plus or minus 1. Only. Yeah. No, can't see it because I haven't put it on. Right. Yeah, okay. So generally false except if n is plus or minus 1. Does n divide n? Always true? Yeah. So even when n is 0, right? So always true. What about n divide n squared? Always true? Yeah. Okay. Because, well, n squared is a multiple of n, right? N squared is n lots of n. As long as n is an integer, it is true. The GCD of 0 and n. N. I've got votes for n. I've got votes for 0. Right. Okay. Time for some audience participation. Who says n? Who says 0? Who says, I don't know, I didn't put my hand up. Oh, sorry. Who says, I don't know? Who says, I didn't put my hand up? I mean, it's a bit contradictory, right? Who says, I didn't put my hand up at that time either, so I could go here for a while. Right, okay. What are the common divisors? What are the divisors of 0? 0. So 0 divides 0, right? Does n divide 0? Does n divide 0? Yes. Yeah, right. All right. Who says that n divides 0, but the GCD of 0 and n is 0? I don't know. We're going to. Okay. Okay. So remember the definition of divides. Let's go back. Let's wind this back. The definition of divides. Right. M divides n if n is some multiple of m. Right. So here our m is n and our n is 0. Right? Is 0 some multiple of m? Yes, it is. Right? 0 is 0 times n. So n divides 0 for all n. Right? So n is a divisor of 0. It's also a divisor of n. Right? So therefore, the GCD of 0 and n is n. I hope. Yeah. Well, technically, it's the absolute value of n. Okay. Can two even integers be relatively prime? No. Why not? Two will always be a common factor of even integers. So the GCD will be at least 2. It could be higher, but it will be at least 2. And finally, I'm not going to advance the slide because I know it's not staggered. What can we say about m and n if LCM of mn is equal to mn? Right, m and n are positive here. Yep. Relatively prime. Yep. So m and m are relatively prime. Right? Why is that? Because, well, LCM times GCD is mn. Right? So if LCM is equal to mn, that means GCD must be 1. Right? And that's exactly the definition of relatively prime. What about if LCM mn is equal to n? N is a divisor of m. M is the divisor of n. Which one? M is a divisor of n. M is a divisor of n. What do we want to say? Who wants to say that and who wants to say that? Okay, votes for 1. Votes for 2. Votes for didn't put my hand up. Right. I think we had a narrow majority for this one, but it's actually this one. Yeah, right. M divides n. Right? Because it's the least common multiple, remember? Right? So they both need to be multiples of n, Right? So n needs to be a multiple of m. Yep. If m is 1, in this case, if m is 1, we could say that, yes. That's not as general, because if m is 1, n is still a multiple of m. But if m is a multiple of n, then if n is a multiple of m, then m doesn't necessarily have to be 1. Right? So what you've said is correct, but it's not fully correct. Yep. So m must be a divisor of n. Right. Okay. So hopefully that sort of like gives you more practice. We'll see a lot more about divides coming up throughout. But perhaps let's look at the first sort of computer sciencey thing around. It's known as the Euclidean algorithm. It was invented by a guy called Euclid about 2,000 years ago. It is arguably one of the first algorithms ever devised. And this is an algorithm for actually computing the GCD of two numbers. And it gives a nice, easy way of doing it. Right? So what you do, if you look at these two numbers, if they're the same, then that's the greatest common divisor. That makes sense. The greatest common divisor of 5 and 5 is 5. If they're different, well, either one's going to be larger than the other. And so what you do is you subtract the smaller one from the larger one and compute the process again. Right? Now, so there's an interesting... This is, you know, as I said, the first algorithm. In a course of algorithms, it's a very nice thing to present because it highlights a few key points. So one thing it highlights is the idea of recursion, which we'll talk about in a couple of weeks. Right? Basically, to solve this problem, I turn to a smaller problem and solve a smaller problem. Right? And that problem, solving the smaller problem, will turn to a smaller problem, will turn to a smaller problem, and so on and so forth, until we get down to what's known as the base case, right? Which is, you know, the smallest problem, and I will solve it, and then it will all go back, and we'll go through this process in a bit. So it talks about recursion, and an interesting side note about recursion is that, well, for algorithms, we always want algorithms to actually stop, right? So it's no good having a recursion if basically you never get to the base case. And so in a somewhat more detailed description, in a more course that would more focus on this, you would deal with the trying to establish the fact that this algorithm terminates. But fundamentally, it's relatively easy to see that it terminates because basically at each step we decrease. So if m and n are positive, we're always decreasing, you know, either m or n. So if you like, we're decreasing the sum m plus n. Right? That is going down. It's strictly going down, and it can't go below 0, right? Because everything is still positive, right? When we subtract the larger number from the small number, we still have a positive number. So this thing will always go down. As it can't go below 0, so eventually it must stop. Right, so that's the sort of arguments that you need in the courses on algorithms for showing that your algorithm stops. So this algorithm terminates, but that doesn't help us very much if the algorithm actually doesn't compute the right thing. And so the next thing you have to do when confronted with this is actually prove that your algorithm works. Right? So this algorithm does something, right? And we'll walk it through in a little bit. But the key reason why it works is this observation. Basically, the GCD of m and n is equal to the GCD of m minus n and n. Right? Those two things are equal. And how do we prove that? We need to prove this result in order to show that our algorithm actually correctly computes the GCD. So the proof is quite nice. First, we're going to establish this. So this is an if-then thing. But I'm actually going to establish a slightly, if you like, a proof a little bit to the left, a little bit to the side, right? And this is an if and only if type proof, right? So I need to prove that If this is the case, then this is the case. And then if this is the case, then this is the case. Right? Remembering what we talked about on Monday. So what I'm going to show is that I'm going to show that if D divides M and D divides N, then D divides M minus N and D divides N. Right? So I already know that D divides N, so I'm not actually, all I really need to do is show that if this is the case, then D divides M minus N. Right? And then I'm going to show it the other way around. And why does that give us the result? Well, remember this is so I take the greatest of all common divisors between M and N. Right? So if D is a common divisor of M and N, then D is going to be a common divisor of N and M minus N. And if I do an if and only if I go the other way as well, that means that if I have a common divisor between M and minus N and N, then that's also going to be a common divisor of M and N. Right? So basically, all the common divisors between M and N match the common divisors of M minus N and N. Right? So all my common divisors are the same, so particularly the greatest common divisor must be the same. Right? So that's how the proof that's how the proof works. I'm going to establish this result here, and it's an if and only if result. Right? So I need to assume the left-hand side and prove the right-hand side. So, okay, so assume. Right, so this is for this side, this implication. Right, assume that D divides M and D divides N. Right? Okay, so this is how proofs work. This is how the sort of thing that you would have to answer on an assignment or in the exam. All right, so this is how I expect the proofs to go. Right, so we're proving this direction. So we assume D divides N and D divides N. Okay, what does that mean? Right, really, that's the first thing you should do. It's like, well, what does D divides M and D divides N mean? Well, that means that. So therefore, well, in order to extract the final result, I need to sort of unravel the definition a little bit. So what's the definition? D divides M. That means that M is equal to some multiple of D. Right? And N is equal to some other multiple of D. Right? For some AB in Z. Right? So M and N are some multiples of D. Now, what am I trying to get? I want to show that D divides N. Well, I already know that D divides N, so that's fine. I also want to show that D divides M minus N. So I need to show that M minus N is a multiple of D as well. Right? So what do? I say, right, okay, well, let's look at M minus N. What is M minus N? M minus N is, well, it's AD minus BD. Right? Which is A minus B times D. Right? Since A and B are integers, A minus B is an integer. Right? Since A, B are in Z, A minus B is in Z. So therefore, M minus N is equal to some integer times D. If you like, where K is equal to B, A minus B. Right? So M minus N is equal to some integer times D. So therefore, D divides M minus N. Done. So assume D divides M, D divides N. Therefore, D divides M minus N. And, well, D divides N by assumption. Right? So I've proven that if this, then this. Okay. There we go. Okay, now I want to go the proof in the opposite direction. Right? So now what's my assumption? My assumption is that assume that D divides N and D divides M minus N. And I want to show that D divides M. Okay? So again, we unravel the definition and try and get to something that we can then apply the definition to. Right, so D divides N. N is equal to some multiple of D, and M minus N is equal to some multiple of D as well. right? That's just the definition of divides, if you like. You can add that and say definition of divide. Right? If you want to be more verbose in your descriptions. So m minus n is c times c. Right? What is m? Well, m is just m minus n plus n. Right? Which is just that's just going to be CD plus BD, right? Which is C plus B lots of D, and again B and C are integers. So B plus C or C plus B is an integer. So therefore, I'm just skipping the K bit, but therefore D divides M. And as before, D divides N is part of the assumption. Right? So that's it. That's my proof. Right? Right? So now I've established that D divides M and D divides N if and only if D divides M minus N and D divides N, which therefore gives me the result that I want, that the GCD of Mn is equal to the GCD of M minus N and N. Right? So this step here, going to this step here, is valid. Right? And there's nothing, these two things are actually symmetric. Right? Everything's symmetric. We can sort of argue that if we do this step, the same argument applies. Right? So fundamentally, that's it. That's the proof of correctness. So this thing here will compute, because it terminates, it will compute the GCD of M and N. Right, and I've highlighted a little bit of the proof there, and I've left a little bit of blank on the slides. One thing to note about this proof is that you can actually replace M minus N with M minus some multiple of N, M minus Kn. Everything still goes through. Right, if you go back to the proof and it's like I replace Kn, right, what you end up with is instead of A minus B, you get A minus K lots of B, right, which is still an integer. Right, so M divides Kn, and then this direction is a little bit trickier. But so this will be important later on. We'll come back to that reason. But basically, the GCD of M and N is equal to the GCD of M minus any multiple of N you like, including one multiple of N, including zero multiple of N, of course. So just to work through an example, so let's compute the GCD of 45 and 27, which is 18, 9, yep, it's 9, right? This is 9 times 5, this is 9 times 3, right? 18 doesn't divide 27. Right, so we want to get 9 as the answer. So GCD of 45 and 27. So Euclid's algorithm tells us, so what I'm going to do actually is I'm going to freeze that one so we can see the algorithm. Right, and then hopefully, no, I froze the wrong one. How did I freeze the wrong one? Right. That's very interesting. Right. Okay. There's the algorithm up there. I'm going to work through it here. So GCD 45 and 27. Is 45 equal to 27? No? Good. Right. At least one person is paying attention. So I apply. So it doesn't apply to the first rule. Is 45 larger than 27? Yes. So I take the second rule. I subtract 27 from 45, which is 18. And so I get the GCD of 45 and 27 is GCD of 18 and 27. GCD of 18 and 27 is 9, right? So good. It's still right. So this was 9. It's still 9. Is 18 larger than 20? Is 18 equal to 27? Is it larger? No. It's smaller. So we go to the third line. Subtract 18 from 27, which is 9. Right. We get the GCD of 18 and 9. Right. 18 and 9 are different. Subtract 9, I get GCD of 9 and 9. And that is now, I'm now applying the first case because 9 is equal to 9. And I get that the GCD is 9. So at every step you notice that the GCD of the two numbers we've got is always 9. All right. So that's one example. Here's a more stupid example. Right? The answer is going to be 4. Right? What do? Well, which one's larger? 108 or 8? 108. So we subtract 8 from that. Which one's larger? Well, we're going to subtract 8 from that. Which one's larger? Right? So, right, eventually we'll get down to 4. So I said it's more stupid. It's more stupid in the sense if we're doing it manually. Right? It's harder. But a computer, of course, will just sit there and churn away and give me the answer. So it's not. So from a mechanical point of view, it's fine. Right? It's just a pain if you're doing this manually. No, don't turn the image off. All right, so we're going to get to GCD of 4 and 8, which then goes to 4 and 4, which goes to 4. Right, so this process, this is still, in terms of computing, this is actually still relatively fast. We'll talk about that a little bit more when we talk about probably recursion. We'll talk about big O notation in 2 weeks, 2 different weeks. So we'll cover it when we do recursion, and I'll talk about what I mean. Why do I mean that this is still actually technically efficient? But it's a pain. So how do we do better? Well, the best way to do better is to sort of introduce more notation. No, it's not the best way to do better, but some very, very useful notation that I have. So this is the third time I've presented this course. This is the first time I've actually remembered to include this this step, these definitions. These are two. This is very computer science, so this is not in the book. The book is mathematical. So 2 operations: the mod operation, the div operation, and one mathematical concept which is also related. Right. So div is integer division. Right. Essentially, if we have integers m and p and a positive integer n, although you can talk about div with negative integers, but for the sake, we'll just do a positive integer. So m div n is basically the integer division of m over n. So it's like you divide m by n and you take the floor. Right? It's essentially what's the number of times that n can go into m completely. Right? So 9 div 2 is 4. Right? Because 2 can go into 9 4 times. It can actually go in 4.5 times, but we don't count that half. So it's like, what's the number of times n can go into m completely? Mod, which a lot of computer programs, a lot of programming languages use the percentage sign, so that's why I've used the percentage sign here, is the remainder of m on division by n. So if we divide m by n, what remainder do we get? And we can actually compute that using div. Right? Remember, m div n is the number of times n goes into m completely. So if we multiply that by n, we're going to get some number which is probably less than m. Right? So if I take m to be 9, right? 9 div 2 is 4, as we discussed. 4 times 2 is 8. Right? So 8 is the if you like, this thing here is the largest multiple of n, which is smaller than m. Right? And then we subtract the multiple of n, which is smaller than m, from m, and then that gives you the remainder of m on division by n. Right, so m mod n, we write it like this, is m minus the smallest multiple, which is smallest multiple of n, which is the largest multiple of n, which is smaller than m. So these two are computer science notation. Mathematicians prefer to write it like this. So they say m is congruent to p mod n. So modulo means ignoring this bit. right? In general English, in general Latin as well, right? So we're saying m is the same as p, ignoring like up to multiples of n, right? Up to multiples of n. So you can sort of say like, 13 o'clock is the same as 1 o'clock up to multiples of 12, right? So it's the same idea. So m is equal to m is congruent to p mod n if you subtract, or you take the difference of m and p, and n divides the difference. N divides the difference of m and p. Right, and then so a couple of quick observations, and I'm not going to give proofs of these. I'll leave that to you guys. If you take the mod operation, m mod n, you're going to get an integer in the range 0 to n, 0 inclusive, n exclusive. Right, so this is the remainder of division by n, so you'd expect it to be a number between 0 and n minus 1 inclusive. How does congruence modulo n relate to the mod function? Right, m is congruent to p mod n if and only if m mod n is equal to p mod n. Right, so this thing, the mod operation gives you the remainder. This thing here just says that the remainder on division of n is the same. Right? M when you divide by n gives you a remainder. P when you divide it by n gives you another remainder. They're the same. So for instance, 13 and 15 are congruent mod 2 because they're both odd. But 13 mod 2 is 1 and 15 mod 2 is 1. So they're also both congruent to 1. Right? So that's how this thing here is sort of like, if you like, more general than this thing here. This is an operation that gives you a number. This thing here is, again, a yes-no thing. Is m equal to p modulo n? And finally, the reason why mathematicians like this notation is because it's very well behaved. Right? If m is congruent to m prime and p is congruent to p prime, then m plus p is congruent to m prime plus p prime, and m times p is congruent to m prime times p prime. Right, so you can take two things that are congruent and add them together, and you still get things that are congruent. Right? And you do the same with multiplication. And we'll see that in the examples coming up. So first, some exercises to work through. So 42 div 9, 42 mod 9, minus 42 div 9, minus 42 mod 9. And then, true or false, is a plus b mod n equal to a mod n plus b mod n? 42 div 9, 6, 4, right? 9 times 4 is 36. 36 is, right, 9 times 5 is 45, right? So divide 42 by 9, you get 4 and a bit, right? So you take the floor of it, you get 42 mod 9, 6. Minus 42 div 9, minus 5, good. I'm hearing lots of not minus 4s, thankfully. So minus 5. Right, remember we take the floor. Right, so when we have negative numbers, right, it goes down. Right, this is minus 4 point a bit. Right, so you get minus 5. And minus 42 mod 9, right, and an interesting sanity check, right, 6 plus 3 should be 9. Right, because technically this is also minus 6. But mod operation, remember, is between 0 and n minus 1. Right. Is a plus b mod n equal to a mod n plus b mod n? Let's say always. Right, who says true always? Who says false sometimes? Wow, that was I think we had like majority of 1 there. Right. It's almost true. It's almost true. Take the example I had before, say A to be 13 and B to be 15, right? So 13 plus 15 is 28. 28 mod, so I'll take n to be 2. 28 mod 2 is 0. 13 mod 2 is 1. So 13 mod 2 is 1. And 15 mod 2 is 1. And 1 plus 1 is 0. Right, okay, no. It's 2. Right. Yes, you came all the way to university to remember that 1 plus 1 is equal to 2. Hopefully that wasn't assuming too much. Right. So it's not quite right. We can correct it because 2 mod 2 is 0. So if I mod that whole result, then it'll be right. And I leave it as an exercise to show that that's the case. Right? So if you take A mod n plus B mod n and then mod n the whole thing again, then you'll get the same as A plus B mod n. Common error in computing, actually. I've done it myself many times. It's just like suddenly I'm working in modular arithmetic, and suddenly I'm looking at a number that's larger than it should be. So a very useful trick. Always take the mod n of everything after you've done everything. Right. Next one. Next slide. All right. Sorry. Yep. No, I'll leave that. So let's do some more computations. Right, now I think hopefully it should become apparent that the last 2 questions, there's a trick to them. Right? Because I don't want you to compute, 10 to the 2019 is 1 followed by 2019 zeros. So I'm not going to expect you to divide by 7 and see what number you get. So there's got to be a trick to that one. And the same thing applies to the last question. What's the last digit of 7 to the 2019? I don't want you to compute 7 to 2019. I want you to identify the trick. So what is the trick? Well, first of all, what's 10 cubed mod 7? 2? Right? Okay. So it's mod 7, so we've got 7 possibles. So who votes for 0? Who votes for 1? Who votes for 2? Who votes for 3? 4? 5? 6? All right, we've got some votes for 6. Right. How do we get 6? Right? Well, we can compute 1,000, we can divide it by 7, and we can get the remainder. No, there's a nice trick. Right? What's the trick? We make use of this result here, right? That if we multiply 2 congruent numbers, it's the same as multiply 2 numbers is the same as multiplying their congruent numbers, right? So what's 10 mod 7? So 10 mod 7 is 3, right? So 10 cubed is just 10 times 10 times 10. So mod 7, so 10 times 10 times 10 mod 7 is going to be the same as 3 times 3 times 3 mod 7. Right? Much easier to work with, 3 times 3 times 3. And in fact, what I can do is I can do the first multiplication, 3 times 3, and that's 9. And 9 is 2 mod 7. So I don't even have to compute what 3 times 3 times 3 is. What I can do is I can just say, right, 3 times 3 is 9. 9 is 2. Right? And now I get 2 times 3 mod 7, right? Which is 6 mod 7, which is just 6. Okay? This is what computers do. This is how you work in modular arithmetic. You don't need to compute out 10 times 10 times 10, 1,000 and divide it by 7. What you do is you simplify things whenever you can, right? So 10 is congruent to 3, so let's just shrink it down. I'll do the first multiplication. I get a number that's bigger than 7, I can reduce it down. Right? Now how do I go from 10 cubed to 10 to the power 6? Well, yes, it's 1. Okay. Is there a trick from going from here to here? Square it. Right? So 10 to the power 6 is 10 to the power 3 squared. Right? So 10 to the power 6 mod 7 is equal to 10 to the power 3 squared mod 7. Right? Which we just worked out was 6 squared mod 7. Right? 6 squared is 36. So we get, this is 36 mod 7. 36 is 1 more than 35. 35 is a multiple of 7. So this is 1. Right? Now, hopefully, the trick for doing the third one should be apparent. Or hopefully, right? 2019, right? Every time I have a power of 6, I basically get back to 1, if you like, if you think of it that way. 2019 is what? How many multiples of 6 is that? Right, is 330, 18, 21, 3, 9, 6. 336 times 6 plus 3. Yep. Right, why did I do a multiple of 6? Well, right, let's write this differently. 2019, 10 to the 2019 is, well, 10 to the 336 times 6 plus 3, right? Which is, it's 10 to the 3 times 10 to the 336 times 6, right? That's just index addition. Hopefully everyone can still see, right? Yep. And this is 10 to the 3 times 10 to the 6 to the power 336. Okay, so hopefully that step's okay with people. It's just a recap of index laws. I will assume that you know how to do those, even if it's a case of just trying to refresh your mind. Right, so 10 to the 2019 is this mess. And of course now I can mod 7 everything. I know that 10 to the power 6 mod 7 is 1. Right, so this thing here is all going to just reduce down to 1. Because it's 1 to the power 336, which is 1. So I'm just going to get that 10 to the 2019 is equal to 10 to the 3, and I've already happened to have computed 10 to the 3. So this is equal to, so when I mod 7 everything, I get, this is equal to 10 to the 3, which is just 6. Okay? So again, that's the sort of tricks that we employ in computing to do these large modulo powers. And computing numbers modulo, or computing high powers of numbers in modular arithmetic is relatively easy to do. Right? We don't have to do much computation. At no point did I compute anything more than a 2-digit number here. Right? The highest number I've got on this page is 36, apart from 2019. Right. What about the last question? What's the last digit of 7 to the 2019? 3. Right. How do we get that?
So the last digit of the powers of 7. We keep looking at the powers of 7, and the last digit starts to cycle after 4.
Okay, the last digit starts to cycle after 4. If we look at powers of 7, right? So 7 squared is 49. 7 cubed. It's not visible anyway. 7 cubed is 243. 343, sorry. And 7 to the power 4 is something or other ending with a 1. Right? And then so 7 to the power 5 well, this 1 is going to get multiplied by the 7, so the digit is going to be 7 again, right? So the numbers cycle. But in terms of the stuff that we've done already, what's going on? What are we looking? What are we looking at this number? Yeah, but modulo, what in terms of modulo, how can you describe it? Yeah, so, I mean, so, yes, you're right, we can look at the power of 2019 modulo 4, but I'll get back to that in a second. In terms of, I mean, how does this question, how does the last digit of this thing here relate to the previous question? Yeah, exactly. So the last digit of a number is given by the remainder modulo 10. Right? So basically this question here is asking what is 7 to the 2019 mod 10? Right? So if I want the last digit of a number, I just look at assuming the number is given in base 10, I look at the number modulo 10. Right? If I want the last 2 digits, I look at the number modulo 100. If I want the last 5 digits, I look at the number modulo 100,000. Yeah, 10 to the power 5. Right? So modular arithmetic can give you some information about very large numbers without actually having to extract the entire last number. So what's going on here? Well, it's the same thing. You said we're looking at the last digit. Right? The last digit cycles around. Right? Well, what's going on? Well, 7 mod 10 is just 7. 7 squared mod 10 is 9. Right? 49, the last digit. Right? 7 cubed mod 10. Right? It's 9 times 7, which is 63, which is mod 10 is 3. 7 to the power 4 mod 10 is 3 times 7, which is 21, which is equal to 21 mod 10, which is equal to 1. Right? And so that's why it cycles around, because now 7 to the power 5 mod 10 is equal to 1 times 7, which is 7 mod 10. And so we're going to cycle around. And so we do exactly what we did before, 7 to the 2019. So now we notice the cycle happens every 4. So we write 2019 as a multiple of 4. Right? It is 50. Thank you. 504 times 4 plus 3. Right? Because next year is Olympic year. Right? So this bit here, so it's going to be 7 to the power 4 to the power 504 times 7 to the power 3. Right? And if I do everything modulo 10, I'm going to get 7 to the power 3 mod 10, which is just 3. So this is where the mathematics comes in easy. I can just write that. That is equal to 3 mod 10. Or is it congruent to 3 mod 10? So the last digit of 7 to the power 2019 is just 3. Cute trick. Useful in computer science when you want to find out some information about things. Right. The last lot of exercise, or the second last lot of exercises, I'm going to leave. But again, it's the same idea. Well, I'll just do one quick hint to how to go about this. Right. It's about identifying divisibility rules. So hopefully a lot of you are familiar with, well, if I gave you a number, you could tell me if it's even or odd, right? There's a nice rule that you've probably learned from primary school. You just look at the last digit, and the last digit's even, and the number's even. If the last digit's odd, then the number's odd, right? The same thing happens with multiples of 5. If you look at the last digit, if it's 0 or 5, then it's a multiple of 5. If it's not, then it's not. You also might be familiar with the rule for division by 9, and there's a similar rule for division by 3, right? If you add up the digits, if it's a multiple of, if you add up the digits and you get a multiple of 9, then your original number was also a multiple of 9. And I wonder if you've ever wondered why this works, right? Well, if I take the number, why does it work, right? If I take my, I'll work with 4-digit numbers. So this is a 4-digit representation. It's not A times B times C times D. Right? A is the 1,000 digit, B is the 100 digit, C is the tens, and D is the 1. Right? well, what does that mean? That means that n is equal to a times 1,000 plus b times 100 plus c times 10 plus d. Right? Now, if I look at all this mod 2, right? 10 mod 2 is 0. Right? So this thing here is going to be a times 0, and this thing here is going to be b times 0, and this thing here is going to be c times 0. And so all I'm going to be left with is d. Right? So n mod 2 is just d mod 2. Same thing happens mod 5. Right? Look at mod 5. These are all zeros, so this all reduces down to d mod 5. What happens when I look mod 9, right? They're not zeros, but they're actually all 1, because 10 mod 9 is 1. So 1 to the power of 1. So basically these are all going to reduce to a plus b plus c plus d. So not only do you have divisibility, but you can actually identify what the remainder modulo 9 is going to be by adding up the digits. Right, so take the number 42, add up the digits, 4 plus 2 is 6. The remainder of 42 modulo 9 is 6, as we discovered before. Right? And this is special about 9 inside of base 10. But if I work in, like, say, if I take a base 7 number, or base 8 number, take a base 8 number, the same thing is going to happen for 7 in base 8. Right? Because my base 8 number, this is going to be, if this is a base 8 number, this represents a times 8 cubed plus b times 8 squared plus c times 8 plus d. Right? If I look at all this modulo 7, these are all going to reduce to 1, and I'm going to get a plus b plus c plus d. Right? If you're not familiar with bases, don't worry about it too much. It's just an advanced observation. So anyway, so that's mod and div, and why are they particularly useful in the last 5 minutes? Is I can speed up, from a manual perspective, my Euclidean algorithm by using mod and div, or particularly using mod. Right? So we noticed before, like when I was looking at GCD of 8 and 108, I got a lot of steps, but I'm just subtracting 8 every time. And I made the observation that if I take away a multiple, any multiple, I'm still going to have the same GCD. So what should I do? I just take away as many multiples as I can. Right? So I'm going to take away as many multiples of n as I can, and what I'm going to be left with is the remainder on division of by n, remainder of m on division by n. Right, so I've taken away all the multiples of n I can, and I'm just left with m mod n. Right, so I skip all those individual steps where I'm just subtracting 8, subtracting 8, subtracting 8. I just subtract the largest multiple of 8 I can, and that gives me the remainder of 108 on division by 8, which is 4. And I'm done. So, as before, we have, in order to establish this is a correct algorithm, we need to show that it terminates and that it's correct, right? And to show that it's correct, we need to show that the GCD of m and n is equal to the GCD of m mod n and n. And how do we do that? Well, if we let k be m div n, right, then m mod n is m minus kn, and we fall into the case of the exact case, this case here, right, where I could say I can subtract multiples of n. Right, so basically, so I'll get then this, and then the result follows from the first proof, essentially. So seeing how it works in practice, so let's take the example that took a lot of manual steps. Take GCD of 108 and 8, right? So instead of going 108, or I can go 108, but what I can do is I can look at 100 modulo 8, which is 4, and I can go straight from here to here. I can actually go straight from here to here if I like, which gives me then I can go 4, 4, and get 4 as the final result. So that's it. There'll be a quiz on this material. Will be released on Friday night or Saturday morning, basically 48 hours before Monday's lecture. Multiple choice questions. It's done on WebCMS. I'll put out a notice when it's available.
trouble understanding like this equation right here. So this will determine in the later on, like when we're talking about like 10 to the 3 to this one, right?
Yeah.
That's two related stuff. I'm having trouble understanding this right now. Like, what's the m slash? What does that mean?
It's, so these are just, so m and m dash are just different numbers.
Yeah. Okay. So why will you use m dash then?
Just because I want it to be closely related to m. Like,
So
I want, like m dash is just something that's equivalent to m. It's like, think of m dash as a different symbol.
but it's the same as m.
Yeah. It's like, I'm trying to save myself writing if m is congruent to, if m is equal to p and r is equal to s.
All right.
Right? Mod n is all mod n, right? Then m plus r is equal to p plus s mod n. Right? I'm doing exactly the same thing. This is a different way of writing that.
So
but the point is, I'm using m prime instead of p,
right.
let's write that. Then m plus p is equal to r plus s. Right? So instead of using r and s, I use m prime and p prime just to highlight the connection.
Then I can just read it and try to understand it.
Yeah.
Thank you so much.
The assignment will be released 2 weeks before the due date, approximately. So due date's end of week 4, so it'll be released during week 2. Yep. No, well, about the assignment. When I get the assignment written, then it will be more or less released. So you'll have at least 2 weeks to do it. It'll be due probably Sunday night. So the latest I have to release it is Sunday night at the end of week 2. Probably. It's like if it ends up releasing later, then the due date will be pushed back.
Like for all and
a mistake about
remember for all
and is
and
and is
which we did in the last class.
Oh, sorry. Yeah. Sorry, that's a typo.
We need to
Yep. Sorry, typo. Yeah. Thank you.
where n, m, and p are integers and so on.
We're just trying to confirm with you, like this one will be a proposition, like you mentioned, like this, right? The last statement is a proposition.
They're all definitions.
These are still definitions.
Yep. This is the definition of div. This is the now this is working. This is the definition of the mod operator, and this is the definition of what I mean by m is equal to p mod n.
So Dr. Hunter, how is a definition different from a proposition?
So a definition like this has never been defined anywhere.
Okay.
M equals to p mod n.
Yep. That's not defined anywhere. This notation is never defined. Right? So I'm using this notation to represent this thing.
So this part is the same of this part. Like when this holds true.
No. So the definition of this is this thing here, right?
Yeah.
Is you can replace this thing here with this thing here,
Yep.
right? M minus m div n.